Hi everyone, in next few minutes I'll be giving introduction on our paper towards precise intra-camera supervised person re-identification. First, I'll introduce some background information that helps understand our work. The task of person re-identification is to match a person's image in non-overlapping cameras. Specifically, given a query image, an algorithm compares the query with images in the gallery and retrieves the top-ranked image for the query. For person re-ID, the most common setting is fully supervised, where both intra-camera and cross-camera relations are given, and for each image, the ground truth ID is annotated. Now suppose that we reduce the annotation budget and only annotate images within each camera. This becomes intra-camera supervised setting. Under this setting, the image relations on the same camera is known, but the cross-camera relation is unknown. Our work aims to design an efficient method for the ICS re-ID task. Now, the first problem we need to consider is how to fully exploit intra-camera annotation. In some previous methods, a multi-branch classification network is adopted, where each branch is responsible for classification on the one camera. However, the potential problem is that the number of intra-camera images for each person is very limited, and parametric classifier may not be properly learned due to underfitting. To deal with the problem, we propose to use non-parametric classifiers instead. Specifically, we construct an ID-level memory bank and design camera-specific non-parametric classifiers. In addition, we also design a quintuplet mining loss for hard negative mining, which enhances the learning and exploitation of intra-camera annotation. To enable the learning of non-parametric classifiers, we construct an ID-level memory bank, which is updated in an exponential moving average form as shown in equation 1. Then we compare the batch image feature with the memory feature to obtain the intra-camera classification probability. A cross-entropy loss as shown in equation 3 is then computed as the intra-camera classification loss. Additionally, we also design a quintuplet loss, which aims to mine the hard samples both in batch and in memory. The quintuplet loss is shown in equation 4. It consists of a local in-batch triplet loss and a global memory-based triplet loss. By enforcing the quintuplet loss, the intra-camera ID, the intra-ID compactness, and the inter-ID dispersion are further improved. The intra-camera learning exploits the intra-camera supervision to learn a base model. However, the inter-camera relations are not explored yet. Since a person may appear in multiple cameras, it's necessary to infer the cross-camera ID relations so that the model learns to recognize cross-camera persons. Therefore, we construct an ID graph and choose graph edges that satisfy the following two constraints. First, the higher similarity usually indicates higher likelihood that two intra-camera IDs belong to the same person. And second, each ID has no positive match on its own camera, and at most one positive ID matched on any associated camera. We set a decent threshold and construct graph edges that satisfy multiple constraints, which are assumed to be reliable. Then we search for connected components in the graph and assign each component with a unique STU label for model retraining. The overall framework mainly consists of 4 parts: the inputs, the feature extraction backbone, the intra-camera and inter-camera learning part. For inter-camera learning, which is also the retraining step in the last slide, the cross-entropy loss and triplet loss are adopted to train the model in a fully supervised fashion. In ablation study, we analyze each component in our method and find that each component is useful. The full model, as indicated by M4, reaches comparable performance with our supervised upper bound on Market and Duke. In Table 3 below, we show the precision and recall of ID pairs discovered by our inter-camera association strategy. We find that precision is quite high, and the recall is over 74%. This shows that the associations are quite reliable. Finally, we compare with the state-of-arts, including fully supervised, unsupervised, and intra-camera supervised methods. From the comparison, we can see that our method outperforms the existing intra-camera methods by a clear margin, showing that our method is effective and promising. That's the end of the presentation. Thank you for watching.